In the next subsection, I want to introduce the first non-trivial compression method, and these are the Huffman codes. Huffman codes basically exploit the observation that some letters, some characters occur more frequently than others, and we would like to take advantage of that. What we'll do for Huffman codes is that we'll fix a binary alphabet. So we'll only consider these. It's possible to generalize Huffman codes to other alphabets, but the most important application anyways is to represent characters by binary bit strings in a computer. So we will focus on this part. And that means we can just write sigma for the source alphabet and drop the subscript s. Now, if you look at English text, then you find roughly these frequencies for characters. I guess that is, I think the numbers sum up to 100. So what that means is these are only the characters, ignoring punctuation and space, etc. Also, spaces are probably even more frequent than E. But even if you remove all the punctuation, you see that this first column makes up the majority of all the text, and then the last column hardly ever occurs. Just, I don't know, 1 in 20 characters maybe. A bit more, but not much. So we would like to assign to these infrequent characters a much smaller, a much longer code so that we can use a shorter code for the ones that occur very often. And indeed, this is also what the Morse code did. It had the shortest code for E, if you remember, and A was also short. So the frequent letters got a short code because people realized this very early on, that this is just more efficient, more convenient. But the task now will be to do this in a more well-founded way. And this is what Huffman codes can do. So Huffman coding starts with a source alphabet and weights. Now these weights could be frequencies from a given source text. So we just go through the text and count how often each character occurs. Or it could be probabilities if we have some assumption that the text is generated randomly and we know roughly how often each character occurs, how likely each character is to occur. So what we assume here, just for making this formal, is that we have a function that assigns a weight to every character in the alphabet, in the source alphabet, and that this is a non-negative number. The goal is to compute a prefix-free code, and by what you've just seen in the previous subsection, that means compute a code trie for this alphabet that minimizes the length of the coded text if each character occurs that often. So what we do is we sum over all the characters in the alphabet. We take the weight of the character and multiply that with the length of its code word. And so if we choose W of C as the number of occurrences of C in S, then this term is exactly the coded text length. Okay, and that is what usually Huffman codes are used like. You determine the frequencies of characters, and then you compute a Huffman code for these frequencies. So this is also where you see this is adaptive to the source text, but it's a single code. So it's the static character code case from previous subsection. That's what I just said. So it's a best possible encoding if we want to encode character by character and want to be able to decode character by character. If you think about it, this sounds really ambitious, right? We want the best possible encoding for the text from this fairly wide class of all possible character character encodings. So knowing that Kolmogorov complexity is so hard, so that we cannot even compute how small we can compress something, we might feel that this is quite ambitious and doubt whether it's even possible at all, let alone efficiently. But it turns out, in this case, restricting to character by character encodings is a substantial restriction that makes a very efficient algorithm possible. So the answer is yes, and even more, a greedy approach is enough. So if you've seen an algorithm design class, you might have seen the greedy, design paradigm of greedy algorithms, where you're always taking a locally optimal choice and fix that and then continue. That usually doesn't work. For many more complicated problems, this does not give you an optimal solution, but here it actually does, and in some other cases it actually does. So what does Huffman's algorithm do? The first step is you find two characters that have smallest weights. So these are the least frequent, least important characters. So those are the ones where we're happy to give them a long code word because they don't occur often anyways. So you find two of these, the one with the lowest frequency, the lowest weight, and then the one with the second lowest weight. And we will encode them using some shared prefix. Their code words will be the same except for the last bit where we distinguish them. But they will share some prefix u that we don't know yet. U is still to be determined. But we will fix for now whatever u will be. We will encode A as u0 and B as u1. Okay? And this choice, or this decision, restricts the choices for the other code words, as we'll see in a substantial way. But it's done by choosing the two lowest weight characters. We never lose the optimality of the overall code. The next step is, now that we've decided how to distinguish A and B, we no longer need to keep both characters around. Instead, we create this super character that stands for A or B. And so I'll just draw this by putting a box around AB. And we assign this super character the sum of the two weights, because it actually stands for both A and B. And once we've done that, we made the input smaller. We reduced the size of the source alphabet by 1. We combined two characters into one. So we can now recursively apply the same algorithm, and it will terminate because we always get rid of one character. When this recursive call terminates, when it returns, it will have computed some code try for the remaining alphabet. So for sigma, where we replace A and B by the super character, in particular, it will find a code word for this AB character, and that will be our U. That's the algorithm. Let's see a small example in a second. I just want to add one remark here. This description is very high level, doesn't tell you how to do these things, especially the first step, how to find the lowest weight characters. But one easy way to do it is using a priority queue. So this is, again, jumping back to Unit 2, Fundamental Data Structures. We talked about priority queues and binary heaps back then. And this is one application for such a priority queue. You initially throw all the characters into the priority queue using their weight as a key. Then the first step just executes two delete min calls on the priority queue. That automatically gives you the two characters with lowest weights. And step 2, where you compute this sum of the super character, you compute the sum of the weights, you just insert a new character, the super character AB, and use the sum of the two weights as key. And if you keep doing this, you will, as soon as the priority queue has only one element left, you know that you're done. And by keeping track how you paired things up, you can reconstruct the tree. But let's see that in an example. So here's a small example. We start with the source text lossless. That means the alphabet has 4 letters, A, L, E, L, O, and S. And we can count how often each of these characters occurs. So we have 1 E, namely here, we have 2 L's, we have 1 O, and we have 4 S's. So we initialize our priority queue. This is the queue all the time. You see what it contains. It contains the original characters and their frequencies, and will contain the super characters while we're going. So we first find the 2 with smallest weight, that's E and O, and now we combine them. Now what we will draw here are actually little code tries. And indeed, a single character is a valid little code try, namely a single leaf that contains nothing else. Now, in each step, we take the 2 little code tries that have the smallest weight. In this case, it's these 2 leaves. And we create a new code try by taking those 2, the old 2 tries, and we add a new root to form a new try that contains both of these. So if we do that here, we take E and O, form a new try out of these by creating a new root and adding these tries as children. And the weight that this new try has is the sum of the original weights, so 2 in this case. And that's how this algorithm continues. We again find the 2 tries that have the least weight, the 2 delete min calls. Here it gives us EO and L. And we put them together by taking those 2, here they are, these are the previous ones, and adding a new root to it. And that gives us the try for the super character EOL. So maybe this is worth noting. Here in the old notation, I would have said we create this super character EO. Okay. In the next step, we create a super character out of the super character of EO. And we add the L. So we have this little nested super character. And indeed, the super character still encodes the entire shape of the tree. But you can also draw the tree. That's a more natural way to represent it. We have one more step to do. There's still 2 tries, but not much more of finding minima to do. It's just 2 tries left, so this is easy. Again, we combine the 2. Here are this is the previous try, this is the previous try, add a new root, and then we have a code try for the entire thing. Let's draw again the super characters just to make that explicit, and that's a format that I also used for the tutorials. So it's convenient if you already know it. This was the previous, this was the S from the other try, and then we just draw a box around this again. Okay, so that's the super character that represents this entire try. And that's the final result. That is the Huffman tree for this alphabet with this with these weights. That is the code try for this Huffman code. And if you now encode lossless using this code, again, for encoding, remember it's more convenient to list the codes as a table where you list the characters and then the code. So let's just briefly do this. E is 3 zeros, L is 0, 1, O is 0, 0, 1, and S is just a 1. Once you've done this, encoding is fairly easy. L is 0, 1, that gives you this. Then comes an O, that's 0, 0, 1. Then come 2 S's, so that's just 2 1s. Then we have another L, so 0, 1. then we have an E, 3 zeros, and 2 more S's. If you correctly count, then you would find that these are 14 bits that we use to represent lossless now. Whereas previously we had 8 characters out of a 4-character alphabet. So we could use 2 bits to represent each of these characters. That would even work out nicely because it's a power of 2. But that would need 16 bits in total. So what we've achieved with Huffman coding here is a compression ratio of 88%, which is not too bad for such a tiny example. There's a caveat though. We would have to also transmit the code or the try in one way or another. So this is, I don't have that on the slide, but I think we should add this as a remark. You also have to store the code try. If we don't do that, then we wouldn't be, if we don't store the try as well, then the decoder wouldn't know how to decode this text because it doesn't have access to the character frequencies. Now, having said that, you can decide whether it's more efficient to store the try or store the frequencies. Generally, the tree contains a little less information, so usually storing the try, the code is more efficient. But if the frequencies are as small as in this case, maybe it's more efficient to store the frequencies indeed. Now, when it comes to Huffman coding, you will notice that Huffman's algorithm is in a sense ambiguous or non-deterministic because it doesn't tell you in this step here in case there are ties, several characters with lowest weights, it's not necessarily clear which one to take. And also, let me make this green, so just to signal. So in this first step, Huffman's algorithm doesn't specify which minimum weight character to use. And here, when forming this, we could as well have used B first and then A. Now, in this tiny example, it looks like it's obvious because A is before B, so it would make sense to use alphabetic order. But remember, this is in general a whole code try, so you have to find, it's not always so obvious which one makes sense. So these are ambiguous. Any choice gives you an optimal code try. But it's often convenient to fix a certain rule so that we all get the same try. Then you can only transmit the frequencies, for example, and everyone executing the algorithm would end up with the same code. And in particular, for our module, should this arise at some point, should someone be asked to do this in an exam, say, it would be important to follow these rules. So we break ties as follows. When selecting the 2 characters in step 1, we always use the ones that come first in the alphabetic order, or the little try that contains the smallest alphabetic letter. And you can trace the example that this is also what we did. So in step 1, we break ties by using alphabetic order, and we use the smallest character in the entire try. For step 2, when we combine 2 trees of different values, when we combine two trees, when they have different values, we break ties by the value. So we put the lower valued tree on the left. The only case that remains is if the two tries have the same weight, then we place the one with the smallest letter to the left. Okay? So this sounds complicated. It's just spelling out all the potential cases where ambiguities could arise. And this is one way to break ties. In this case, there could be others that are just as sensible, but please stick to this one whenever it comes up in this module. You will have an example on the tutorials for next week where we practice this a bit, and that also will follow this convention. So just adhere to it. Now, we've claimed that Huffman's algorithm finds a best possible code, but I want to briefly sketch also why this is the case. So formally, we have a theorem that given any alphabet and weights for that alphabet, Huffman's algorithm computes the best possible code. And formally, it computes a prefix-free code that minimizes this L of the code words, which is this this expression, the sum from before, summing of all characters, their weight times the length of the code word. And I want to sketch this proof just very briefly, because this is not the focus of this module. Basically, you start with any optimal prefix-free code. Because it's a trie, it has to have two leaves that are somewhere at the lowest level and are siblings. So this is somewhere deep in the tree. And these are at maximal depth. Now, because it's a Huffman code and in a trie, notice that we can always swap around the letters. We can replace one character by another, and it remains a prefix-free code. So what we can do is we swap characters that have lowest weight in the total alphabet and put them in place of X and Y. Because we take lowest weight characters and we swap them for X and Y, and these were at maximal depth, that can only make the code better overall, make this L smaller. But because we started with an optimal code, it means that we still have an optimal code. So it's an alternative optimal code. Now, if we combine these two things and essentially replace this with the super letter, so we don't have these two, but instead we put here the leaf XY. That makes the alphabet one smaller. And any optimal code for this smaller alphabet where we use the super letter yields an optimal code for sigma when I just replace these again. Because we could start here with any optimal code and we could modify it in that way. So we can get whenever with any optimal code for the reduced alphabet, we get back an optimal code for the entire alphabet by expanding out the XY super character. And then finally, because the recursive call yields an optimal code for the smaller alphabet by the inductive hypothesis, that means we also get an optimal code for the bigger alphabet. That was a very brief proof sketch why Huffman's code is actually optimal. It's very much following the algorithm through, and the magic thing here happens because we do an induction. I left out the induction basis if we just have a single character, but that one's easy too because Huffman's algorithm doesn't really have to do anything in this case. So with that sketch, let's leave this theorem 7.1 for now. and just conclude that Huffman's algorithm always computes a prefix-free code that has the minimal expected code word length as defined here.